Hello, this is Mrs. Hedden, and we're going to look at notes for Chapter 14. This is just the first set of notes on this chapter. From Derek's video that you just got done watching, basically Derek's video is really a repeat of the Chapter 13 content. The important thing is our perception of temperature is really based on how fast heat is conducted. And Derek's demonstrations really depended on that zero law of thermodynamics. That is, by resting the two objects in question, the book and the hard drive, in the same environment, they were all in thermal equilibrium, meaning they were all at the same temperature, technically, as determined by a thermometer. But perception-wise, which is very, very powerful, everybody said, well, no, the metal is colder. And that perception of that metal being colder, even though they were sitting in the same environment, is why that zero law of thermodynamics, which looks so simple, is actually really, really groundbreaking. Resting two objects in the same environment, they're in thermal equilibrium. Despite what our perception is, they are at the same temperature. So the next question is, and what Chapter 14 deals with, is do those two objects contain the same amount of heat? Conceptually, we understand that heat is proportional to temperature. The hotter the temperature, the more heat. But if two objects have the same amount of heat, if two objects have the same temperature, do they contain the same amount of heat? We know, and then from the video on James Prescott Joule and William Thomson, or Sir Kelvin, there's some important engineering things that were going on, and some of the first science was thermodynamics. At first there was the engineering, the steam engine, and they admit nobody really knew why it worked. They didn't understand it, they just knew it was there. They knew that heat was doing the work, but they didn't understand how much or why. So Joule established that there is a mechanical equivalent to heat, and that energy is conserved. The amount of heat you had was equivalent to the amount of work done by the system. Heat transfer produces the same effect as work. Therefore, they're equivalent. And that's conservation of energy, and that's big. Similar to the idea that work done on a system can change its potential energy, temperature or heat transfer done on a system can change the amount of internal energy it has. So taking this argument one step further, heat must simply be another form of energy. And that makes sense. If heat is a result of the movement of atoms, molecules, or particles, and movement is kinetic energy, then heat must be energy. Now, because we measure heat differently, because those chemists got to it before we did, but it's still a form of energy, it must relate to the joule. And so we have this relationship that 1,000 kilocalories is equal to 4,186 joules. So 1 kilocalorie is about 4.2 joules. Okay? But there's far more that comes from that video. What Joule was first working on, that electric motor, what he was really worried about is, can I make this battery-operated motor as effective as a steam engine? Well, that's the same thing that the guys who want the Tesla cars to work are worried about. And why wasn't it as effective? Well, Joule discovered that the temperature would increase as it was trying to do work. The entire battery would increase. And if the temperature was going up, then the heat, which we know is proportional to temperature, must also be going up. And if the heat is increasing in the body of the engine, that heat was not being used to do work. And that rise in heat was causing a leak in the energy in the system, just like friction. The essence of saving energy is to prevent leaks of energy. That's why LEDs and fluorescent bulbs are so much cheaper to run than incandescent. Incandescent bulbs get incredibly hot. They're leaking energy. They're losing it. And likewise, most of the money you spend on gas for your car really goes to making your engine hotter rather than making you travel farther. Cars are incredibly inefficient. The other thing that was in that second video was Carnot. I can't say his full name. He's that Frenchman guy, briefly mentioned. What Carnot did is he tracked and described the work done the heat lost, and the efficiency of a thermodynamic system. The result of that we call the Carnot cycle, which is a concept of how heat is circulated through an engine to do work. But to understand the Carnot cycle, which you're going to have to understand, we must first understand how heat flows. And that gets us to some basic questions. Well, how does heat flow? Is the temperature, if the temperature is the same for two or more objects, we know they're in thermal equilibrium, but do they contain the same amount of heat? So what does heat depend on? What does heat flow depend on? And how and why is heat transferred? And what controls that rate of heat transfer? But there's no real way to determine how much heat an object has. Just like we can't say how much work an object has. We measure work by how much is done by the object or done on an object. Likewise, we measure how much heat is transferred to or from an object. Just like work is energy in transit, heat is energy in transit. And so we call it heat transfer, or Q. I know we used Q in fluid dynamics, and Q is in this chapter the rate that heat moves at, just like the Q in fluid dynamics is the rate that fluid moves at. And that gets us to the very simple formula, Q equals mc delta T, where Q is the heat transfer or heat flow. And the units can be in joules or calories. Both are units of energy. Typically, a calorie is a very small unit, so you'd have a kilocalorie, and you may well end up with a kilojoule, because a joule is a small unit too. That kind of depends. C is the specific heat. It depends on the material, like whether he had the book or the metal hard drive. And the phase, is it a solid, is it a liquid, or is it gas, or is it a plasma? So the phase, the material, an ice cube will contain more heat than a similar amount of just straight water. SI units can be in joules per kilogram times Kelvin, or joules in kilograms times degrees C. If Q is measured in kilocalories, then C would be measured in kilocalories, and that should be a slash, not a question mark. Kilocalories divided by kilograms times degrees C, or times Kelvin. Delta T is a change in temperature, and since the change, not just a single temperature, and since 1 degree Kelvin is the same size as 1 degree Celsius, the units can be in either Kelvin or centigrade, Celsius. Mass, of course, is measured in kilograms. I want to go back up to where I'm talking about joules up here and kilojoules. While typically we have a lot of joules. Let me actually go to a pen. Okay. Typically we have a lot of joules when we're talking about transfers of energy. Because this guy is in joules and not kilojoules, you're going to have to work with joules in your equation, and then you might end up converting to kilojoules. All right, let's go to the problem. It's a very simple problem. The same amount of heat entering in identical masses of different substances produce different temperature changes. In other words, the work done in terms of heat is different for different materials. So, if you have a 0.5 kilogram pan made of aluminum who has a specific heat of 900, and a 0.5 kilogram pan made of copper with a specific heat of 387, and they're both sitting at equilibrium, thermal equilibrium of 20 degrees centigrade or Celsius. Okay. What would each of the final temperatures be if you added the same amount of heat to it? In other words, if you turned the burner on the stove to the same thing for the same amount of time, would they rise to the same temperature? Do they heat up at the same amount? Well, we're going to be using that very simple formula, Q equals mc delta T. Okay, and to make the units work, notice we have joules in the specific heat that I looked up, whereas here I've got kilocalories. Now I could go back and look up the specific heat in kilocalories instead of joules, but that means I'd have to retype this whole thing. So instead, I'm just going to convert kilocalories to joules, because that's easier to do for me right now. So I've got 0.8 kilocalories, and I'm just doing a dimensional analysis. I'm going to zap out those kilocalories, and I end up with about 3,348.8 joules. And then I'm going to figure out the aluminum pan first. And it would have a final temperature of 27.44 degrees. I'll leave the algebra to you. And then I did the copper pan, and it would have a final temperature of 37.31 degrees. So the copper pan does indeed heat up faster than an aluminum pan. And that's all. You have a WebAssign of 1 problem due Monday. Thank you very much for your time.